All right. It's not a quiz, right? Because I'm not grading 5 pages of problems. But there's some practice problems, mostly over naming, moving some electrons around, and some more easy practice. In the earlier folders, there are some practice problems with naming alkanes and cycloalkanes, and I believe Lewis dot structures and resonance structures. So I'll send you an email and point out where those are. All of them have narrated answer keys, so they not only have an answer key that you can look at, but also if you, and I'll send the directions just in case. If you wanted to see the narration, then you can go in and it's just me talking through the problem. And you can go to any problem you want by zooming around. I will create an answer key over the weekend for this that same way. But it probably won't be today. So I'll work on it. It's going to take me a couple hours to do that. But I'll email when it's available. So those are some extra practice problems. And let's see, the chapter 2 in the reading problems are due by 11:59 tonight. And then for Monday, the chapter 2 homework problems are due. Again, I'll start do it at 11:59 every day. Okay, so today was chapter 3. What questions do you have over anything, including chapter 3?
I have a question over, but it's on chapter 2. Should I just write that on a note card or?
No, that's fine. Chapter 2 homework or?
No, it was in the question. I just went back and did the questions, and there was one that I didn't quite understand.
Okay, this is in the reading?
Yeah.
Okay.
It was question 54. I get why it's like 4-sec-butyl, 6-methyl, 5-oxohep, 6. And then my only question was, it says enoic acid, and I'm wondering why it's not anoic acid, because it doesn't have any double bonds in the longest chain. Okay. It's all single bonds.
All right, so this is 56?
54.
54. Okay. Okay, 54.
Yeah.
It's an aldehyde. It's not a carboxylic acid.
Yeah, the one that was 54 on the thing, but it said it was like the answer was like 4-sec-butyl. I wrote down that it was 24. That doesn't look right.
It was within the carboxylic acid chapter. Maybe this one?
Yeah.
Number 59?
Sorry, I wrote down wrong.
No problem. Okay, so what would we name this molecule? Let me transfer it over to the... Okay, there it is. So, again, when we're starting this, what do we have to think about? We should know what functional groups are in the molecule so that we can look at the chart and see, okay, what's the highest priority one? So what functional groups do we have? What? Carboxylic acid. That whole thing is the carboxylic acid. What else? Wait, what's... This should be a double... Stop. There shouldn't be an O there. There's just double bonds. So what else we got? We had a ketone. And what else? The alkene. Okay, so we've got to come up with the longest continuous carbon chain, and it's got to contain the alkene and the ketone, because those are both groups that can be part of the longest chain. But which is the number one highest priority group overall? The carboxylic acid. So it's going to be, that's where our chain's going to start. And that's also where the numbering's going to start. So carbon 1, carbon 2, 3, 4, 5, 6, and 7. So this is going to be a hept. Well, it's going to be a heptene oic acid.
So you include, I thought when you were doing the longest chain, it's only carbon atoms. And that's what determines if it's an alkane, an alkene, or an alkyne.
It is only carbon atoms, and in this case, there's only carbon atoms in the longest chain. But it's got to be continuous.
And you went through the O.
No, it won't go through to the O.
Okay,
So this is a carbon atom. So I'm not including any oxygens in the longest chain.
So if you're going in the longest chain and it's down between a double bond and a single bond, you go with the double bond.
Yeah, the double bonds, triple bonds, and ketones have to be part of the longest chain
Okay, so that's where we first did. Okay.
in these molecules. Right. What else? So that means this one's going to be what? A hept-6-ene oic acid, telling you the double bonds between carbon 6 and 7. And then what alkyl groups do I have? Is that what's coming off for? We all agree it's a sec butyl group? And then we've got a methyl group over here. And then what about the ketone? The ketone is going to become an oxo group because it's basically a substituent. So in terms of the writing then, this would be what? A 4 sec butyl, 5 oxo. No, methyl would come. Methyl comes before oxo. Why won't you let me erase? It would be a 6 methyl, then a 5 oxo, heptene, and 6 oic acid.
The methyl would come before the oxo just because of alphabetical order.
Yeah, it's just alphabetically. Oxo is just a substituent name.
And the sex doesn't count for.
Right, because it's hyphenated. If it was isobutyl, it would be I, because it's all one word. Any need for E or Z or cis or trans here? No? Why not? Because the double bond doesn't have...
Two sides. It couldn't have
we might want to be a little more specific than cutting it in half. There's nothing on the right-hand side.
No double. We're just trying to say no double bond within the carbon atoms.
I wouldn't say that either. There's two hydrogens on one side. Which one? And okay, but what about that having two hydrogens negates the cis trans?
If you were to flip it, it'd be the same thing.
So in other words, whenever a carbon in the double bond has two of the same groups, there's no cis trans or EZ. So in this case, there's two hydrogens, and so there's no, that carbon has the same groups, and so there's no cis trans. Does that make sense to everybody? Now over the weekend, I think I'm gonna put together some key things that you should know at this point. And we're at the end of week 3. So you should know your alkyl groups, common names of the alkyl groups, and how to name the IUPAC names for alkyl groups that don't have a common name. And you should know your functional groups, and you should be able to use the chart in terms of naming. And so I'll bring that on Monday, and you can take a look at it. And if there's anything on there that you're not quite up to speed on, you're going to want to bring yourself up to speed on it. Bobby?
Can you just say again why there's no cis trans?
Because there's these, one carbon has the same two groups. So whether it's like this or it's like this, there's no stereoisomer. If I flip the carbon, if I flip that position, I'm not making a new molecule.
You can't got a double bond because it's not two carbons.
Well, let's imagine that I flipped the other double bond. I flipped the double bond at the bottom. Did I make a new stereoisomer? No, because a methyl's still next to an H, and this group's still next to an H.
Take the O away on the other side, right when the numbering started.
Take,
They just put the other one. You can't use that one if it's not the numbering started after the double bond.
when I'm over here, this is the one that I'm considering to be cis or trans. So it doesn't matter whether, if I interchange these two groups, I haven't made a new molecule. If I interchange these two groups, I still haven't made one because they're both next to hydrogens. So whenever one of the two carbons has the same groups, it's not cis-trans. It doesn't matter which one I flip. What else?
There was another one you had to write the name. It was the only one you had to write.
In the reading or in the homework? In the homework. Okay, let me get out of the book. Go to the homework. You think it's in the 30s?
Yeah. 34, 32.
Oh, that you type in. Did it grade it? Or do I have to grade it? So, this is an ester. So how do we name esters? So I don't think we haven't done an ester in class. The way we think about esters is this. The way you traditionally make an ester is to react carboxylic acid with an alcohol in the presence of an acid catalyst, but we'll talk about that later. You react the acid with the alcohol and you make the ester. So the way we think about the ester is that the ester has an alcohol portion and it also then has a carboxylic acid portion. So as far as naming goes, we always name the alcohol part first, then the carboxylic acid part with either an ONATE, so it's a like butanoate, or if it's a common name, it's just like acetate. So for instance, if I had this alcohol, this ester, so if I had that ester, the first thing I have to do is name the common name of the alcohol part. So what's the common name of that alkyl group? We agree? Isopropyl? Agree? So this is going to be isopropyl. Then this is a 3-carbon chain. So that means it's a prop. And the suffix then for the esters, which comes from the carboxylic acid time, is ONATE. So this is isopropyl propionate, or propanoate. So it's always the alkyl group attached to the alcohol first, followed by the carboxylic acid part changed from an anoic acid into an OAte.
Just to clarify, I know they're two separate groups, right?
Yes. Yes. So that's how we name esters. So we have to go, if we're going to go to that molecule, which, let's see. I should remember exactly how to do this. There's a 4-carbon chain with 2 methyl groups there. Then a C double bond O. No, there's 1 extra carbon on that side. Right, so it's that one. So looking at the alcohol, does that alkyl group have a common name? Everybody have all their common names memorized? So that when you look at it, you say, oh, that's not one I memorized. But that doesn't have a common name. How would I check? Well, I'd go, it has 1, 2, 3, 4, 5, 6. There's only a couple hexyls that are on that list. Straight chained, N-hexyl, and I believe isohexyl. And that's it. That's been accepted as a common name. This isn't either one of those. So now we have to remember, well, how do I name alkyl groups using the IUPAC rules if they're not don't have a common name? So what's step 1? What? That's step number 2. Step number 1 before we go for the longest chain is what?
Any for the longest one.
Nope. I'm looking at an alkyl group. So what's the number 1 carbon?
It would be where the double bond is, right?
Nope. I'm double bond. The double bond's way over there. I'm on the one that's circled. I'm looking at the alkyl group that's circled. We can't go through the longest chain because the longest chain would have an oxygen. So I have to name the alkyl group on the alcohol part first. Right? So my first step would be to do what?
Find the carbon closest where it attaches.
Forget about closest, where it attaches. The attached carbon is number 1. The attached carbon is automatically number 1. Okay? Whenever we're naming an alkyl group here, we're not naming an alkane. So the attachment point is automatically number 1. Now step 2 is let's find the longest chain starting at number 1. So that's going to be a 1, 2, 3, 4. So there's my 4 carbon chain. I'd have to take away that circle and then I could circle it, but there's my 4 carbon chain. So that's a 4 carbon chain alkyl group, so what do I call it? Butyl. So this is a butyl group. Good. And now I can go ahead and number from that carbon, from the attachment. So 1, 2, 3, 4. This is a butyl. Two methyl butyls. Anybody want to give a friendly help? 2. 2, 2 dimethyl butyl. Well, it's like a fire hose of answers coming at me, not all in unison. Which meaning not all the same thing. So it's a 2,2 dimethyl butyl. Okay, that alkyl group does not have a common name. If it was something like tershbutyl or isobutyl or tershpenyl, we would use that common name term. But if it doesn't have a common name, then we have no choice but to use the IUPAC rules. So we have to go back and remember what's those steps. Now the reason that I'm emphasizing the attachment point being carbon number 1 is because that's where the chain starts. If there was stuff attached to carbon 1, the chain would start at carbon 1. It would not go to whatever's attached to it. David? Yes. I don't have the ability to space my when I leave space to put the thing in front of it, I don't have space, so I can't make it match up. So it would be all one word. And it could be put in parentheses because that's the group. So what have I just done? I've named the alcohol part. So now I got to name the carboxylic acid part. So when I look at the carboxylic acid part, if you've looked at the chart, things that come at the end of the chain are at the highest levels of priority. Aldehydes, carboxylic acids. So this part then automatically numbers there for 1, 2, 3, and 4. And so that should be, that's now a 4-carbon chain there. Remember, this is an ester. So I should have a bute, but now how do I handle the double bond? Bute, 3-ene, and now the suffix for esters. And it would probably be OATE. So this would be bute 3-enoate as opposed to anoate. Because anoate means single bonds. Enoate would mean there's a double bond. I suppose you could have an inoate where there would be a triple bond. And in front of the ene, I need a number because I need to know where the double bond is. It's between carbons 3 and 4. The carboxylic, well, in this case, the carboxyl group, the C double bond O group of the ester is automatically given the number 1 priority. And so this is now 2,2-dimethylbutyl bute 3-enoate. That altogether would be the name.
So you have to put the 2,2-dimethylbutyl in parentheses?
No, that's a good question. I don't think so, but I might. Because otherwise, what I don't want to get confused about is if I don't want the butyl to become part of the bute 3-enoate. I want it to stay part of the original group. So parentheses would be okay. Now the problem is how sophisticated is their grading routine? Because you might have already encountered in the lab that if you write in something that doesn't quite match up with my answer from lab, then I have to go back through and grade it by hand, which is why people send me emails, usually starting tonight, when they say, well, I got like 2 out of 20 on the lab quiz, and I know I got them all right. And then I have to calm them down and say, okay, I have to go through and regrade it, because if your answer doesn't match my answer word for word, period for period, space for space, comma for comma, it's not marking it right. So then I have to go through and I have to grade it by hand. I have a feeling these guys are letting me grade this one by hand. So any of the problems that you run into in either the homeworks or the in reading problems, if you, like, we went through 3 of them the other day that were wrong, like the degrees of unsaturation should be 4 and they had 8. Anything like that you find, email me, because I'm going to have to tally those up, and then I'm going to have to go through and correct and add points onto everybody's score, or your score, when I get all this, at the end of each chapter.
So do we not do any naming with the double bonded O?
With the double bonded O, that is the ester part, which is part of the OATE suffix. The OATE suffix says this is an ester. And so it sets the structure of the C double bond O with the O on this side and the carboxylic acid part on the other side. So each functional group is slightly different. This is how you do esters. What else? The 4 kinds of reactions. So the problem with the 4 kinds of reactions is that we're going to learn these in gory detail, very gory detail, but not in week 3. So what they're doing is they're giving you examples of real reactions we're going to talk about and putting them into the 4 categories. So the first category would be substitution. And so if I just write it generically, if I was reacting A plus a molecule where a B part was bonded to a C part, if I ended up substituting A for C, that's a substitution reaction. So one part of the molecule's been substituted for by another part. Okay. We're going to look at several types of substitution reactions. But one of the examples I think they were showing was, let's say I take a bromide and I react it with something like chloromethane, or you could also call that methyl chloride. In this reaction, the bromine is going to replace the chlorine. So this is a substitution reaction because one halogen has substituted for another. And it could be, we could make this a little more complicated, but it's basically one group substituting for another. Now this reaction has a defined step-by-step mechanism, and I think they showed that to you when they were talking about, okay, here's the reaction. It goes through a transition state, and then it goes to intermediates, and then it goes through another transition state to get to the final products. So this is substitution reaction we're going to talk about in all of its glory, and all of its step-by-step how it works. So that's substitution. Then we have addition. And in addition reaction, you add like A plus B, and you make A and B. So you take 2 molecules, you react them together, you get one out. That's an addition reaction. And so I think the example they showed there was, let's take something like HCl and let's react it with an alkene. So when I add the HCl to the alkene, and again we'll learn the step-by-step process here, the H is going to add to one carbon and the chlorine is going to add to the other carbon. So that the final product will have one carbon with 3 H's and the other carbon with its original 2 H's plus the chlorine. So I've added HCl to that double bond to make an alkane. So 2 molecules coming together to make one. So that was their example of an addition reaction. We're going to define this a little bit more. This will be called electrophilic addition. So that's 2. Then let's see. Number 3 is elimination. So elimination reaction, I'm going to take that same one I just did. And if I do something to that molecule, I can actually eliminate HCl from it. Make the double bond. And it spits out HCl. And so that's, elimination is the reverse of addition. Sometimes. Sometimes it's the reverse. And then what was number 4? What? Rearrangement. Yeah, rearrangement. So in a rearrangement reaction, their example was, let's say I have this alkene. Well, we could name that alkene, right? What would that be called? I'm also going to have to make it a priority again to put people's names in my iPad so I can just start randomly calling on people. Cis-butene, close. But notice I'm writing it down, so you're pretty close. Because if I just said no and didn't write anything down, you're out to lunch. Cis what butene? Cis-2-butene. Right? So if you wrote cis-butene, try and draw the structure again, and when you wrote it, you'd be like, okay, where's the double bond go? So that way you know that you're missing the number.
Putting the -2 in between the is not the right way to write it.
Oh, sorry. We're using the other system.
Okay, right?
Yeah, I'll accept either one of those.
Okay.
There's an old and a new way of doing it, and what I just did was the old way. Although they sometimes do the old way themselves. But it really should be cis-butene. Either one I'll accept.
There's only really a double bond you're worried about. That's where you can slide it.
Yeah, you could slide it in front before. You just don't want the numbers to be confusing. So if you put the number right before the group, there's no confusion. If the number moves away from the group, there could be confusion depending on how far away it gets and whether there's another number in there. Bobby. I'm still trying to figure out IUPAC rules. Exactly. They switched it somewhere. They switched it somewhere along the line. Books have changed too, but I noticed in this case, this book uses both kinds. So it doesn't really matter as long as there's a number there to tell me where the double bond is. All right. So anyway, what were we doing? Well, we're doing rearrangement. So cis-butene. How stable do you think cis-butene is? Anything going against it? Well, if I add some acid to it as a catalyst, cis-butene will immediately become trans-butene. And again, we'll learn the mechanism for this later on. I'm not concerned about the mechanism, but this is a rearrangement. So this molecule rearranged its structure. It became the other stereoisomer that we talked about last week. Well, what happened was the H plus as a catalyst helps break the pi bond. We now have free rotation around the sigma bond. And then once it rotates itself and stops, it loses the H plus and we now have the new molecule.
The methyls repelling each other.
So if this is the one that's formed, it's going to be that this one is more stable. And so the question would be, why is the one on the right more stable than the one on the left? And it's because these two methyl groups right here are on the same side of the double bond. Remember, all these are just big balloons of electrons. And so when you have methyls close together, you've got electron clouds repelling each other. That's called steric interaction, or steric hindrance. So if we give this a catalyst, those methyl groups that are not happy next to each other will have free rotation, they'll get far away, and then we'll reform the double bond. So this molecule, while looks good, could be better if the methyl groups were on opposite sides of the double bond. So this one is our rearrangement reaction. And all of those reactions we're going to talk about. And what I think they started to do was they started to go down the mechanisms for each one of these reactions, which I have no problems in doing, by the way. I have no problems in introducing the mechanism now so that we can, then when we go to it later on, I'll just say, oh, well, you remember back then, and I know that you don't remember back then. So we have to go back over it again. But then you've heard it twice, which increases the probability that it sticks. But let's be honest, it doesn't do that much probability increasing, Bobby.
So the only thing that changed for this molecule then, like in naming it, the only thing that would change would be cis.
So the product would be trans-butene.
Okay, that's what I thought.
Yeah. So it just changed the stereochemistry.
Would it be like that all the time, or in some cases would it be able to actually change the molecule?
You know, when we're talking about rearrangement, we're going to be talking about a different type of rearrangement in the future. So then I think they also said, hey, if you have a reaction coordinate diagram that looks like this, first of all, what are we plotting? Energy. I got a better idea. Because I can ask you all sorts of questions. I just pepper you with questions now. And this is called the reaction progress. Right. So let's see, what's my question? Here I'm going to do 1, 2, 3, 4, 5, 6, and then 7 is that. 7 is that. Is this different? Your choice. Tell me what each one of those numbers represents something significant in the progress of this reaction. Your choice. Give me a number and give me what it is. 6 is the activation energy. Okay. Next. Nope, only one answer. One answer per diagram. Close. 7 is the change in not free energy, but because this is energy that's normally in terms of, well, this reaction could be either this thermic or it could be this thermic. Exo or endo, those refer to a change in what? Not delta G, but delta H. So the 7 is the delta H of the reaction, the change in enthalpy.
3 is an intermediate.
3 is what we call an intermediate.
One is reactant.
One are reactants. 5 is the product. All right, I got 2 and 4 left. What are 2 and 4? They're the transition states. I don't know if you use the term transition state or activated complex in general chemistry. General chemistry used to be, it was activated complex. In organic, it's more transition state. So those 2 and 4 are the transition states for the reaction. I have one question. Is this reaction endothermic or is it exothermic? We agree with exothermic? Anybody want endo? Anybody don't know? The reactants have more energy than the products. So what does that mean? That means they gave off energy, and that's what kind of reaction? Exo. What's more stable, the reactants or the products? Products? We agree with that? Okay, products have lower energy, right? So they're more stable. That one works for people too, right? Stability, energy, that's pretty good for people too. So this diagram then is something that we're going to use over and over again. And the only thing that we're going to do is we're going to have to put the structures of each one of these things in the reaction. So what's the transition state of the reaction going to look like? And so we'll have to be able to do that. What's the intermediate of the reaction going to look like? And so, but we have to remember what the basic terms are. So that's good. Okay? All right, on Monday, it's I think it's more in chapter 3, or, well, at that point, any questions about those? And I'll put the answer key up for these, and I'll come up with some roadmaps of things that you should hopefully know or will know shortly after. If you have any questions, shoot me an email or stop by.
Bye-bye.